Hello and welcome to ISY 6382. Today we will talk about improve phase. We start with the concepts of experimental design, and then we learn how to design and analyze one-factor experiments. We learn how to analyze and design multiple factor experiments, and finally we talk about full factorial experiments. And some of them have overlap with ANOVA that we learned before, but some of the techniques are new in this lesson. Okay, let's just start with definition of experiment. Experiment is a test or series of tests that widely used also in engineering world. Design of experiment definition is a formal, structured technique for studying any situation that involves a response that varies as a function of one or more than one independent variables. So it's exactly what we are talking about. Y, which is a CTQ, is a function of some x's. There is a very interesting quote. There is a very interesting quote from Douglas Montgomery saying that all experiments are designed experiments. Some of them are poorly designed and some of them are well designed. Okay, now let me explain basically what design of experiment is and what are the objectives of design of experiments are. So let's say we have a process with output y, and we have some inputs, and we have some factors affecting our process which are controllable, and we denote those factors by x's. Those are some root causes that we can control. For example, if we are talking about a reactor, we can change temperature, we can change pressure, or we can change the type of input material, raw material. Y would be yield in that process. We also have a set of factors or set of root causes which are not controllable. They could be influential, but we cannot control them. For example, in some cases, the environmental conditions or like humidity cannot be controlled. So we denote those by Z variables. What are the objectives? What we want to do in design of experiment, we want intentionally change those controllable factors, or if possible, some of those uncontrollable factors, and see the effect of those on Y, which is the output. So we intentionally want to change that and see that effect. Why? Because we want to identify which variables are most influential. That's sort of like an objective which has some overlap with analyze phase as well. Which x's are most influential, which z's are most influential. And this is very important, the second one. How and where to set the influential x's so that y is almost near desired value. Okay, so let's say the target, we have a target value for y, and the question is, and we know that x1 and xp are important. The question is how we can set the value of x1 and x2. So what are the desired value for x1 and xp so that y is close to target? And it's not always target or nominal value. Sometimes we want to maximize y. For example, we want to maximize yield. The higher, the better. And sometimes we want to minimize y. For example, we want to minimize the number of defects on a surface. The lower, the better. But again, the question is how we can set those influential factors so that we can achieve that goal. The third objective is determining where to set the influential x's so that variability of y is small. So if I want to show you, let's say this is the distribution of y, and this is the target or nominal value. What we want to do, we want to find x's which changes the distribution of y to target and make it on target. And also at the same time, we want to find the values which basically reduces the variance, because we know that the variance is also related to quality. That's another objective. And the last objective is how we can make the process robust. What I mean by that, we know, for example, that x1 and xp are influential factors, and also we have some uncontrollable factors. Let's say z2 is also like humidity. Environment humidity is one uncontrollable factor. So the question is, can I set x1 and xp to a value that optimizes y at the same time it removes or it makes the process robust to change of Z2, which means if Z2 changes, it has a minimum effect on Y. That's another basically objective of DOE, which is related to robust design. Here are some examples of typical application of experimental design. We can use it for improving process yield, we can use it for reducing overall cost, or we can use it for selection of optimal design parameters and robust design. And we have other examples here, as you can see. Let me start with a toy example, very interesting example in real life for golf players. So let's say a golf player is trying to lower his score as much as possible, so the lower the better. Some of the factors that he thinks might be important are listed below. We have type of driver, type of ball, walking versus riding, type of beverages, type of round, time of round, whether it's rainy or sunny, type of golf spike. So some of them are controllable, some of them are not. For example, you can control type of driver, type of ball, walking versus riding, or type of beverage that you use. But you cannot, for example, control weather. Okay, so this is sort of like Z, these are X's, and we want to optimize Y or minimize Y, which is the score of a golf game. So here are the DOE steps. First, we need to start with the statement problem, recognition and statement of problem, what we want to do, whether we, what are the factors, and basically which ones are controllable, which one is not, and we want to minimize or maximize which response. The second step is to define the factors and levels and ranges. So what I mean by levels and ranges, for example, say Y is yield and X is time. And now the question is, what is the range of time of the reaction? Could be between 10 to 80 minutes, and that is defined by the process knowledge that we have or the domain knowledge that we have about the problem. And we say, like, how many levels do we want to define between this range, between the lower bound and upper bound, 10 and 18. Let's say we want to define 3 levels. We want to have 10, we want to have 35, and we want to have, 45, and we want to have 80. So these are the 3 levels that we have, 10, 45, 80. So that's what I mean by levels, and that's what I mean by range. And X is one factor. Selection of response variable, as I said. Choice of design, what kind of design we are going to use. Are we going to use, for example, full factorial design, fractional design? We need to decide on that. We conduct the experiments based on the design that we had, and we collect the data. Finally, we do the statistical analysis, followed by drawing conclusions and recommendations. So what are the DOE principles? There are 3 important principles in DOE that we need to be aware of when we are doing the experiment, running the experiments, and we are analyzing the data. The first one is randomization. So randomization means if you are going to do, let's say, 16 experiments, you need to randomize the order of those experiments. You should not start, let's say, let me give you one example. Let's say we have time at 10 and 15, and we have temperature at, let's say, 80 and 100. Now, how many different combinations we have here? We have 4 different combinations. We have 1080, which is time and temperature. We have 1580. We have 1000 and 1500. So these are different combinations. What I mean by randomization, you have 4 experiments. Try to basically randomize the order of experiment. Do not start from this and then move to this one. So randomize the order and randomly run the experiment. Why this is important? Because if there is any factor that you are not considering, there is any noise factor that you are not considering in your experiment, the effect of that is going to be removed by randomization. So replication. Replication means you need to repeat each combination that you have. At least you need to have two, basically, in most of experiments, you need to have two runs for each combination. Okay, otherwise, the statistical analysis is going to be difficult. There are some methods for the cases that we only have one run, and so that some of the problems are, or some of the design experiments are very expensive. We cannot repeat that. There are some methods which deal with basically these applications. However, in general, we prefer to have replication, because when more replication we have a higher statistical analysis power. Blocking is another one. We talked about blocking in analysis phase. Sometimes we are interested in analyzing some factors. Let's say we are, in our example, we want to see the effect of time and temperature. But there is another factor, which is type of operator working with the machine, could affect the experiment, but is not of our interest. So what we need to do, we need to block that noise factor based on blocking techniques. So these are the three principles we need to be aware of when we conducting the experiment, designing the experiments, and analyzing the results. Here are some terms that we use in design of experiment a lot. First one is factor. One of the variables being studied in the experiment could be either one of the xi's or zi's. There are different types of factors. It could be qualitative, like the type of equipment, methods, or personnel, or could be continuous and quantitative, like a temperature, pressure, or time. But no matter what, we have different levels of x's. Okay, we have response is a dependent variable, such as yield or concentration in a chemical process, and we denote it by y. We have effect. Effect of a factor is if we change x or independent variable, or one of those root causes, how much y would change. That's the effect of the factor. Here is one example. Temperature is x and moisture content is y. If the temperature in the experiment level changes from 125 to 130, we will see a change in the moisture content from 0.24 to 0.19. So the effect would be around 0.05%, and it's a kind of like a negative effect. Okay, that's what we call effect. Okay, we have treatment. A single level of a single factor in an experiment called treatment. For example, when we say time is 10, that 10 is one treatment. If I have two factors, time and temperature, you remember we had 10 and 80, and we had 10 and 100, 15 and 80, and 15 and 100. So each of these two is called a treatment combination in that example. Finally, we have experimental run, which is defined as running each experiment. So each treatment combination, we may run it once or twice. And as I said, the treatment combination is the combination of all treatment, the levels of all treatments. For example, this is one run, one experimental run. This is another experimental run, and so on and so forth. So when we repeat, we also repeat the experimental runs as well. With that, we finish this lesson. In the next lesson, we learn different types of designs and how to analyze the data. Thank you.